Mr. Dalman, you can share your screen. I give you the permissions.
Okay. Okay, welcome everyone. Unfortunately, we couldn't start the main lesson, but let's save time and then continue with our session. My subject is related to quantum computing again, but this time is the combination of quantum computing and also quantum uh, and machine learning. So just brief introduction about myself. Actually, I am from Turkey. Last 4 years, I have been working and living in Sofia in the Commerzbank Technology Center, and I am mainly the financial systems expert. But at the same time, I have been studying and working on parallel, mainly the machine learning and data science subjects. Quantum machine learning also my mostly the secondary uh, subject that I am involving, but I am not working in that area, and also in the bank, I'm not doing related to anything related to this subject. But I just in 2008, when I finished my master's, I just joined the boot camp in the University of Toronto, and I had the chance to learn the hands-on experience related to quantum machine learning systems. And since that, then I've been studying this area also. And time to time, I'm giving the talks in different, events. Okay, when we talk about the machine learning, which is actually the very popular subjects, especially in the name of artificial intelligence, but artificial intelligence is a very big subject that it includes different areas, and one of them is the machine learning. And when we say that machine learning, what we understand is actually using some algorithms or mathematical models so that the system learns the data and its properties. And then by using these models, we use these models to predict or to understand the new data. So this is the main goal of the machine learning. And then here, for example, you can see the traditional programming and also the machine learning subject. On the traditional programming, you can write your own code and then do whatever you want with the computer. But in the machine learning task, actually, you don't know how to define the data. So you analyze the data by using the machine learning model, and then that model later can be used for the prediction. And there are three different sub areas in the machine learning. The first one is supervised learning, and the other one is unsupervised learning. Supervised learning is mostly that we have some data, and also we know that output what we need to as an output, so that we are training this algorithm, this model to for the predictive tasks. For the unsupervised learning, actually, we have the data, but we don't know, and we want to analyze the data, what kind of relations or the templates or what kind of structures in it. So the main reason for the unsupervised learning is this one. And also the recently it came again very popular, the reinforcement learning. And this is more the new kind of learning, that interaction with the environment and then learning and to reach some target. There is another kind of division in machine learning, which is it's called the discriminative modeling and also generative modeling. In the discriminative modeling, actually, we have the data and also we know the outcome, and then we are training the models, and then this model will predict for the new data. So this is called mostly the discriminative modeling. There is also another one, which is again very popular these days. It's generative modeling, means we train with the data, the model, and then the model learns the structure of the data and then generates a new outputs related to this data. That's why it's called generative. And one of the very good examples is this large language models that, they are learning the data and from the text and then replying your questions. So it generates some new output. These are the different kind of machine learning models that we are usually using in different ways. I'm just listing that one. By the way, I'm going to share this slide so that later on you can look at the details of these slides also. And the second part of the quantum machine learning is the quantum computing, and mainly, of course, we are having this training here that what are the main aspects of the quantum computing. I want to just briefly summarize what we are saying and what we mean when we say the quantum computing. We know we have been using the computers, and it's in the terminology it's called the classical computing. So we use the computer to process information, to process data, and we use classical logic gates or classical physics. These gates are based on the classical physics, and then we write a code to process the information. On the quantum computing case, actually, we are using the quantum computing features to process the information. That's why it's called quantum computing. And the main aspects of the quantum computing is, I can say, here you can see all of them. First of all is quantum. One of them is the qubits that we are, the qubits have information and it's superposition, because in the classical physics we have, classical computing, we have bits and we have information in it, and then we call it the one bit information. In quantum computing, the main item is qubit, and it can be a superposition of the different states. In a very basic way, the qubits may have two different states, so it can be a superposition of these states. So the first feature that we are using in the quantum computing is the superposition. The other one is the quantum entanglement, which is the different qubits. Although they can be separated away, they have some kind of correlations in it. I mean, the information in the qubits have the correlations, and this cannot be explained classically. This is the feature of the quantum computing. The other one is the quantum tunneling. Is again not in quantum classical physics we have this feature, but quantum tunneling also is an important feature of quantum computing, and then also it will be used in the quantum simulations and quantum machine learning. The other important part is the measurements, and this is also the different than the classical physics, because in the classical physics the qubit have zero or bit have zero or one information, and when we measure it, it will return one of them and always return the same value. But in the qubit case, we have a probabilistic feature, so that in a superposition case, when we measure the qubit, it may return, depending on the probabilities or weights of these different states, it may return different values. And this is one of the main features of the quantum computing, that why it is so useful and also why it is so difficult, because we cannot control these probabilities, but we can use them for our own purpose. And on this slide, you can see the different kind of qubit structures already. This kind of information covered in the lecture, so I'm going to skip this one. But recently, maybe you may heard that the Microsoft announced that they just achieved the topological qubits, which is very important if it is correct, because there are some discussions about this one. But it's very important advancement if it is correct. And mainly most of the companies are using the superconducting loops here, this one, or trapped ions. And these are the different qubit technologies and used by the companies at the moment, and different companies working on the quantum hardware and quantum software. So they are using different kind of technologies, and this slide shows this one. And as you can see, only the Microsoft is working on topological qubit. Another important thing is on the quantum computing is the quantum computer. Actually, when we say the quantum computer is just like a QPC, quantum processing unit, and it's very isolated environment. It's very sensitive to the environmental conditions, so it's very important to isolate and then keep the quantum properties inside this qubit. So that's why, you know, when you look at these screens, the majority of the hardware in the quantum computer is used only to isolate quantum chip from the environment. And then here, for example, you can say that in which conditions that we should keep this one. And in this diagram, you can see that this is the processor here. It's very simple, very minor chip here, but overall this structure is just create the environment. Why we need this feature? Because in order to use the quantum properties and for our own purpose, I mean the information computing process, we need to isolate this process. Otherwise, Otherwise we cannot use these features, and the quantum devices cannot will be useless in this case. And this is another chip that D-Wave company is using this one. They have a different kind of technology other than the other companies like IBM and Microsoft and other companies. I will mention later of this one. This is the D-Wave quantum processor, and it has 2000 qubits here, a very small area. But these qubits are not the same qubits that we mention usually when we speak about quantum computers, like in IBM cases. And I'm also going to skip this part because we already covered these subjects, that, you know, what are the gates and different kinds of gates in the super quantum computing, and then the quantum computing formalism, you know, the Hilbert space and qubit states. So usually when we read some books or papers or some other documents, we see that quantum circuit method. And the quantum circuit method is very important, that it's like a code that we are writing in the quantum computer, but it's a circuit diagram. So when we say the quantum circuit, something like that, we mentioned this one. These are we have the 2 qubits and 1 classical bit here, as you can see, and the qubits are represented as horizontal lines. So these are the horizontal lines, and the 2 qubit and 1 classical bit. By the way, why we need the classical bit? Because we cannot communicate directly qubits. We need to get the information into first classical bit and then use that one. So that's also another important aspects of the quantum computers. And then operations are represented as gates. In this case, you can see this is the Hadamard gate, and then we are applying some gate operations, and then at the end we are measuring the output from the classical bit here. And the qubits do not flow along the circuit. This is actually the time on the horizontal axis shows us the time. So we are just assigning the qubit values and then applying the gates and then reading this one. So usually when we see this circuit model, we can read out what is the meaning of this circuit and what is it doing and what kind of operation is doing on the circuit model. You can look at these diagrams and try to understand that way. And that's another a little bit complicated gate model again. And at the end, you see, we have always the measurement, because we need to measure the qubits and then get the classical information. Otherwise, it will be useless for us. And another important aspect for the quantum computing is NISQ, which is the noise intermediate scale quantum computing. Why we need such kind of age or the definition? Because the qubits, still many companies, including the IBM, trying to develop hardware related to qubits implementation, but it's really very difficult because, as we mentioned before, we need to isolate the qubits from the environment, and then it should be noise free in order to be used for the information processing. But at the moment, we don't have fully noise free qubits. So the many companies, including the IBM or Microsoft, they are trying to achieve this goal. But at the same time, in 2018, John Prescott, later I will mention that he just come up with an idea that, okay, we don't have noise-free or the really very trustable qubits, but maybe we can still use these qubits for our own purposes. So he just come up this idea, which is noise intermediate scale computing. And at the moment, you can see that many companies using this terminology and trying to use the current state-of-art quantum computing hardware, which is, of course, at the same time, on parallel, many companies are trying to make it more fault-tolerant quantum computing. But it will take some time. And as you can see here, it says that within 5 years, but it's already past the 5 years, and we are still struggling to reach this the target. But in the future, I believe we will reach this target. At the moment, we should keep up with the current technology and how we can use this current technology for our own purposes. And this is another slide from the IBM and the other hardware developers. As you can see here, the IBM, Rigetti, Intel, Google, these are the hardware producers related to quantum bits, and they are trying to reach more and more qubits at the same time. Why they are trying to put more qubits on the quantum processor? Because we need more quantum qubits to use for some meaningful or useful purpose. This is also related to IBM roadmap. You can look at here. There are some numbers here. You see that at the moment, this is the qubits that they reach, but they are scaling. They want to scale up to 10,000 to 100,000 qubits, which is required for some meaningful and useful application. What are these ones is here. If you look at here, what is the key potential applications related to quantum computing, and what is the approximate qubit required here? By the way, these qubits are logical qubits, and there is a distinction between the logical and then physical qubits. Depending on the noise level, around approximately 10,000 physical qubit can be only one logical qubit, and one logical qubit is important, and because we need to to somehow scale that, how we can use the qubits for our own applications like machine learning or optimization. And these qubits are logical qubits, so just consider that when you multiply these numbers with for each logical qubit 10,000 physical qubit, it's a very huge number. That's why they are trying to reach that level. And why we need these distinctions? Because of the error, the noise in the quantum systems that we need now. In order to compensate these error levels to the acceptable levels, we need that much higher number of the physical qubits. And there are different kind of applications. As you can see, the machine learning will be one of them, but there are also the unknown problems. So this is a open case now. What kind of new things that we can apply the quantum computing are very important. And there are some groups also working on this one. For those who are interested in the quantum algorithms, very good. There's a very good website here, quantumalgorithms.org. You can look at many theoretical developed, developed theoretically by some mathematicians and quantum scientists. Most of them is theoretical purpose, but some of them is can be used for some meaningful way. So it's a, it might be a good idea to look at what kind of algorithms they are working on this one, and you can look at this web page also. And then, and also you might hear that the quantum supremacy, quantum advantage kind of words, uh, like the Google just announced that we not now but several years ago I think they say that we achieved the quantum supremacy and something, but here you can read also these definitions, but the important one is the quantum advantage, because why we are developing these systems and algorithms, solution of a valuable problem. We are trying to reach that one. So it should be that way. There are some other ways that they show the quantum supremacy, but we cannot use any valuable problem for these algorithms. But they are more theoretical research study, I can say. But the advantage is important, like in different areas, that how we can use the quantum computers and then get this advantage over the classical computing. And these are the different kind of the companies at the moment working. Some of them is already unfortunately closed because this slide is a little bit late, but most of them is still operational. You see here the hardware and software stuff, and also there are some companies for the application side. They are trying to use the hardware and develop new quantum softwares, and also we have enabling soft technologies also. Now there are additional companies every year. There are many new companies, startups are opening. So it is impossible to keep up this change. But the important one is, of course, we have to develop trustable hardware and software, and then they will start using this one. And this is quantum computing platforms. This is also a little bit late, but there might be some additional. But it might give you an idea to what kind of things that we have. You see, we have the hardware level and then assembly level, like the QSM. But after that one, some companies focus on only developing some quantum softwares, like the Google, Xanadu, Rigetti, D-Wave, IBM. They have different levels of products they have, starting from the hardware to the programming languages. Here, for example, IBM Qiskit, Rigetti, Forest, Xanadu is Strawberry Fields, and also they have a Penny Lane package, Google side, Circ, and then Microsoft Q Sharp. So you can look at these ones. And what is the difference and relations between the conventional computing, which is we call it classical computing, to quantum computing? And the conventional one, we have the CPU, we have the memory unit, this is called actually von Neumann architecture, because it was first designed by the von Neumann after the Second World War, I think. So, and on the right side, you can see the quantum computing system, and then we have some hardware level qubits there, and then we have the algorithms, and we are just using this hardware to run this algorithm. And there is also communication or integration between the quantum computing system and then hardware system, the classical system, because we need those information through the classical information as a classical information. And mainly now the quantum machine learning algorithms are using this feature. So they are running the part of their logic in the quantum computer and then get the results and then process it. I will show these examples also now. So I'm just going to skip this one. So what kind of, the quantum algorithms that at the moment user. Actually, there are two main ones that measure. One of them is the quantum annealing, and the other one is the gate model. Quantum annealing is mainly not used for, not accepted as a quantum computing, but it's more the, how can I say, the optimization software. So they have some problem, then they are just transforming to some kind of Hamiltonian in the quantum system. This is quantum computing terminology, and then they are implementing this Hamiltonian in the quantum chip, and then run the system, and then get the result. So this is main idea behind this technology. It is used only for the optimization purpose, because it's not a general purpose quantum computing. And this is the reason that they are using this kind of system by using the quantum tunneling feature from the quantum mechanics. They want to solve, and they want to find some solution to the problem. And here, by using the tunnel effect, the system moves to the solution part. And D-Wave is actually the major player in this area. And they have, as I mentioned before, they have 2,000, I think more than 2,000 qubit system. But these qubits are not the qubits like IBM's qubits. They are more their own structure, and then you need to design your algorithm mostly like a graph kind of problem, and then you need to apply this algorithm to this qubit structure and then get the results. So this is mainly used for optimization problems. So you need to transform your problem to graph problem to apply on the D-Wave system. This is one of the requests. The other one is the gate model computers, and here we have the quantum algorithm, and then we transform it to some quantum circuit, and then quantum compiler is transform this circuit model to some instructions, and then send to quantum processor, and then get the result. And so why we mainly interested in the quantum machine learning? There are three main reasons that I can say. The first one is classically is really very difficult problems that we might be using, like there might be some really very complicated problems, and okay, we have some heuristic solutions, but they are taking so much time and then so much effort, and also not always giving the correct answer. So we hope that we can use quantum computers features, these, the superposition and other kind of features, to solve this kind of problems very quickly and very efficient way in the quantum computers. One of them, these ones. And the other one is, again, can we speed up some algorithms that currently we are using? So because of, again, the quantum computers, not always, but in some ways can speed up or may speed up some algorithms. And then we can use for that purpose. And actually, there is a third one, which is, I think, the most important one. What are the new algorithms that we can come up and use the quantum computers? At the moment, up to now, mostly some classical algorithms, the implementation in quantum computers. But these new algorithms that using fully the quantum features might be more exciting in the future. And to my knowledge, I don't know much this kind of algorithms at the moment. In the future, I think we will have more. And then we have more qubit systems. In the quantum machine learning methodologies, we use mainly these noisy intermediate scale architectures, like mainly the quantum neural networks or variational or parameterized circuits. And then what are the algorithms related to this one? One of them, for example, the distance estimation. And these are the machine learning models. And if you work on these machine learnings, you will see that distance estimation is very important. And then we can use the quantum algorithms to do this kind of calculation in these models. So in some complicated calculations, we use the quantum chip, but the remaining one, again, will be on the classical side, or clustering, or dimension reduction. These kind of things are mainly the machine learning models that mainly we are using in the daily life. But in some part of this one, the quantum machine learning methodologies can be very efficient. And this is the main study in the quantum machine learning. And then here, for example, in the classical machine learning, you can see that we have the raw data, and then we have a model, and then we train it by using the optimization algorithm. And then at the end, when we finish it, we use this model to use the new unlabeled data, and then we get the predictions. So this is the main usage of the machine learning model. We have a training part, and then we will use for the validation part. For the quantum machine learning, again, this is a schematic representation of the standard quantum programming workflow. I can say here, you see, you have some libraries and stuff, and then you define your problem, and then quantum language like a Qiskit and kind of things, and then you create a quantum circuit, and then you should have some compiler to send these instructions to quantum device and then get the results. Usually in our work, you have seen that one also. You may not use directly quantum device, but there are also quantum simulators. So all these companies, I mean, software providers, they have a direct connection to quantum device, but also they have libraries for the quantum simulation. So you can use these simulators to develop your own algorithm. And these are the general overview of the quantum machine learning algorithms, as you can see here. At the moment, we don't have the fully quantum machine learning. We have the hybrid quantum machine learning. I'm going to explain now what is this quantum machine learning. And these are mainly the quantum neural networks, quantum kernels, and then quantum optimized problems. So by using different quantum algorithms and the models, as you can see here, neural networks, one of them also. And then we mentioned this one also, quantum annealing. So these kind of the different techniques that we are using or trying to develop in quantum machine learning algorithms. The most important, actually one of the most important part is how we are going to encode the data. So when I say the encode the data, we have the data, which is, again, we call it classic data, but we need to feed into quantum computer. Then that means we need to encode this data into qubits. In a more, the fancy language, we have to project this classical information into Hilbert space information in this case. So there are different ways that we can use this one. So we have the classical data, let's say some input values from some system, and then transform into quantum computing qubits, I can say, because then once we put into qubits, then we can start process this information. So that's why this encoding is very important, and there are different ways. When you start working on the quantum machine learning models, you will see this kind of different encoding techniques. Here, how we are using this one, which is, I mentioned here, you see the hybrid approach. That means, the quantum computers and the classical computers are together. We are using together. So on the first part is to prepare the quantum data set. So when I say the quantum data set, actually I'm using this encoding techniques from the classical data to quantum qubits information. So this part. And then we have the actual quantum circuit model here that we are processing the information. And then we have, at the end of this processing information, we are measuring this outputs. Again, we need to get this information on the qubit information to classical information. And then we are processing them and doing some calculations on the classical side, which is on the rightmost part is the classical side. And then we are going to update some parameters here. And as you can see, these phi1, phi2, phi3, these are the parameters that we need to update. Why we need to update? Because this algorithm on the left mode is trying to compare what is the calculated result and what is the expected results, and then there is an error between them, and then this is we usually call this one cost function in machine learning, not specific to quantum machine learning. And then by using this cost function, we are going to update the circuit model parameters. So that's why this is called the variational model. So we are just updating these parameters and then trying to reach some minimum cost level. So this is the mostly used in the machine learning model. Try to reach some minimum level error in the machine learning model. And so this is a general approach, I can say. It's called the hybrid approach, the classical and quantum part. And one of the example is this binary classifier. Here, for example, this is a classical circuit. This is a circuit model, as you can see here. And these phi's are the parameters. You see the phi 1, phi 2, phi 3. These are the different parameters in the gates. And at the end, we are measuring the output from the system. And then by using this output on the cost functions, we are just calculating the new values for these phi values and then update them and then run this circuit again. So there is a loop here with the feedbacks. And whenever we reach some acceptable error level, the system stops. And then now we just train this system. So what is this model here? These are the parameters and then circuit model. Then you can start using this model as a quantum machine learning model to predict something. So binary classifier is in machine learning is, we are trying to classify in two different sets, like some spam or not spam, for example, in the emails. Or always you have two different class and you are trying to predict what is the class of the input values. So this is an example for this quantum machine learning circuit model. And the other one is this is a neural network model this time. Here again, it's using the binary classifications, and as you can see, is the encoding part also very important. So we have different kind of data encoding from the classical data to qubit, and all of them have different kind of effect on the output of your model. So there are many studies related to this one. Which one is good? In which case we have to use this one? That's also another study subject that I can say. And I'm just skipping this one. And this is also one of the most used the approach is the variational quantum algorithm, and how we are using this one in this method. Again, this is the hybrid method. I mean, the quantum part and then classical parts. And what are the different ways that we can use the quantum computers? Is of course the first idea when the founders suggested quantum computers as actually the simulations, because they want to simulate actual quantum systems by using the quantum computers. And simulations mainly like the enzyme or drug design or protein folding, all these kind of stuff, molecular or atomic level, that how we are going to simulate those quantum systems. Why did they suggest this one? Because the classical simulations used to be very expensive, and in some cases it is almost impossible, to simulate this kind of systems. So quantum system might be very useful. The other one is the optimization. We mentioned this one. Like you say, the optimization, supply chain optimizations, and the finance risk management, or scheduling and logistics, which is again includes the robotics, traffic and routing, autonomous driving. So these kind of things are mainly focused on the optimization. You don't need to write a really very good the gate model, but you need an annealer or some quantum optimizer. And the machine learning, of course. As you can see, there are many ways that we can use this one. I have also some comments related to this area. At the moment, mostly academic. There are some companies in finance and in logistic, in transportation. They have some research and development departments that they are trying to develop their own quantum computing algorithms and then try to apply their own business. These are all research and development ways and many startups, but to my knowledge, there is no real commercial applications at the moment, quantum computing or quantum machine learning, but hope is very much. And the educational resources, it's really increasing. We have every year we have more and more documents about this one and books and also the boot camps, GitHub repositories. So we have including the IBM ones, of course. And the field is really very large and very complicated. There are many, many things that you can work on this one, like the computations, cryptography, hardware part, control, error corrections, software development. Of course, physics and maths, they are very important. But there is a negative side. It's lots of hype, meaning, the too many misconceptions related to some results, and also usually because of this internet age, some terminology easy, the just they transfer from this kind of information. So we have to be careful about, when we are reading these studies and then things, and there are really different, very important the experts in this area. We have to follow their comments, their talks, their seminars to get what's happening in this area clearly. Because too much hype is not good. Actually, it creates too much false hope, I can say. And in terms of skill sets, these are my suggestions to you that, at the moment, actually, I have been working more than 5 years in this area, hands-on, I can say. On the quantum computing side, of course, the mathematics, mainly the linear algebra, and of course, the basic quantum mechanics, not the advanced one. And then by using this one, we are going to learn the basic quantum computing. And again, the important one is the algorithmic and programming skills, because we are going to write the codes and then we are going to test these algorithms. This means much practice, meaning learning these techniques and then try to use these new skills and tests to write and develop our own codes. On the quantum machine learnings, there is additional ones, which is the optimization, because the machine learning is, mainly the optimization. So optimization is important. We have to, the classical optimization is important to learn this one. Again, mathematics. And but when you learn the machine learning, you learn also optimization. So learning the machine learnings from good source, like the university, or very good book, and some videos, it will be very important. Again, the good programming skills are very important, I can tell you. These are some project ideas that you can look at and then try to search in internet. You will find many examples, like from the Monte Carlo simulations to some image processing, credit scoring, and I have found very good examples that I am going to share with you as a paper later. Credit scoring, for example. And these are the some my suggestions that you can follow. These first two guys, the Feynman and Yuri Manin, is the main father figure of the quantum computing. But they started to this idea as a simulation, but because they want to simulate quantum systems. So, and then John Pascal is still very active. This is very quantum information scientist. So you can look at his webpage and then his lectures in YouTube and in his university. It's very important. Scott Aronson is again one of the very trustable figures in this area, so you can follow his blog. He's very good in this area. Actually, he's very trustable, so that many papers they are sending him to evaluate those papers. So it's independent. So it's not the working with a company. So you can imagine that he is more independent from the market, so that he can very openly criticize if something wrong. So you can trust him. And then Peter Vitek is actually this person is one of the founders of the quantum machine learnings, and he was my friend. But unfortunately, he is dead now because he was a very good climber. Unfortunately, one of the expedition accidents, he lost his life. But you can find his video lectures and also the books in the internet to start for the quantum machine learning. It will be a good practice for you. And I think, yeah, I just suggest as a starting point these two books, which is the most related to computing, which one of them is the Feynman lectures on computations if we are interested in the quantum computers, but don't expect that the current quantum computers, but this is the beginning of that one, and it will be very good. I suggest you can read this one. And again, the Scott's book is the quantum computing. This is not a technical, but it's more informatory book. So it's a good starting point. Then you can move on to more advanced and then technical stuff, because you should have a good base to work on this idea, the new field. I can tell you. And I think, yeah, I finished my presentation. I was a little bit quick because uh, because of I have some limited time, but I hope I'm not over this one now. If you want, if you have any questions, I can answer your questions.
Thank you, Mr. Delaman. It was very interesting again.